Jnanam Paramam Dhyayam. Knowledge is supreme.
Hello students, welcome to the last week of this course. In this week we'll be focusing on two topics which are of importance in terms of process control. In the first half of this week we'll dedicate our time to what is known as multivariable control, and the later half will spend on batch process control, because controlling a batch process is involves a lot of additional things than what we have been looking so far, which was very easily applicable to continuous processes. So, let us get started with multivariable control, and here are the objectives for this particular portion of this week. So, first I want you to learn, or so be able to state that why it is important to look at there is a need for multivariable control. Then you should, if you have a system which has multiple variables, then you should be able to assess the stability of that particular system. Then if you have such a system, how do you compute whether those control loops interact with each other or not? How do you quantify interactions in the system? And lastly, how do you pair any specific input with a corresponding controlled output? So, we will see all those things as we move along in this particular week. So, in order to motivate this, let me first start with a comment that so far we looked at control algorithms when we had a single controlled variable and a single manipulated input. Now, let us keep aside some of those traditional advanced controllers where we had certain cases where we had more controlled variables and few manipulated inputs, or the other way around. But other than that, so we were still eventually what we were trying to implement was that when it comes to the final PID control or the final control law, it always dealt with one controlled variable which has its own set value, and one manipulated input which will be used to reach that particular steady state value or set point value. So, all those were known as seesaw strategies, which means single input, single output. But when it comes to a real process, you will rarely have a single variable which needs to be maintained or controlled at its value, and you will rarely have a single manipulated input dedicated to it. Let us take an example of a CSTR. So, let us say this is a CSTR, and you have certain feed which comes in, you have a jacket around it depending on what sort of reaction it is carrying out, exothermic or endothermic. You would also have a product valve. So, if I want to see what is the main control objective for this system, then I definitely want to controlled variables. As this is a CSTR, I have put this CSTR to achieve a certain amount of extent of reaction. So, the objective would be either composition at the outlet or the temperature inside the reactor. So, this will be sort of an inferential control strategy if I want to use temperature to infer the composition. So, that is one controlled variable. Additionally, in order to make sure this reactor does not overflow or does not drain down, you would also have volume or level control. So, you will also have a level control into this particular process, and then in terms of manipulated inputs, you can have the coolant or the hot fluid flow rate. So, let us say if it is a coolant, then you will be putting in cooling water here and it will come out here. So, your manipulated inputs can be your cooling water flow and the outlet flow. So, this is F out. So you can see that even for a simple system like a CSTR, you will have multiple controlled variables and you will have multiple manipulated inputs. And what you can realize is that if I change some of these things, so let us say if I change, if your volume or level inside the reactor has to change, so your F out, which is the outlet flow rate of this reactor, would change, and when it changes, it is ultimately going to affect the purity or temperature inside the reactor. So it is not that when you have these two controllers, they will also have some sort of interactions within them. For example, this F out, which is a manipulated input, affects both the level as well as the composition or temperature inside a reactor. So that is why in a real process, what you really end up having is known as a MIMO, which is multiple input, multiple output system. So let us take another example here. So here what I am showing is inline blending. So you have two streams, two pure streams. This is some component A and this is some component B, and they are mixed together to achieve a certain final blend quality, which is known as a final composition, and a certain flow rate of that particular stream. So there you can notice that there are two control variables. One is I want to control the final composition, and I also want to control the final flow rate. And the two variables which you have here is the flow rates of these two streams. So you can see that this is a MIMO system. There are multiple inputs and multiple outputs. In order to control this type of system, there are two broad categories of control structure which you can implement. What I am showing you is that I have dedicated one manipulated input to control one particular output. For example, the way it is shown here, I am controlling the composition. This AIC is a composition controller. So composition is controlled by using this stream W1, and the flow rate is controlled by using the another stream which is W2. So I am dedicating one manipulated input to one controlled variable. When you do this, this is known as a multi-loop CISO strategy. So if I want to do MIMO control, so if I have MIMO system, there are two ways I can control it. One is I can dedicate one input to each output, and I can have a control loop around it. So you will have multiple such control loops depending on how many control objectives you have, and it is known as a multi-loop CISO strategy. Or I can have a single controller which sort of has two controlled objectives, like maintaining W as well as X, and simultaneously it will change W1 and W2. So that is known as a pure truly a multi so MIMO controller. This is known as a MIMO controller. So real multi input multi output controller, which will be something like this. So it will take in both the inputs, both the control variables, it will take in both the set values, and then accordingly will give you the two inputs. In terms of a CISO strategy, what you have is you will have one controller which is dedicated to Y1, and you have a second controller, so this is C1 and this is C2, dedicated to U2. So that is the fundamental difference between a multi-loop CISO strategy and a fully MIMO control strategy. So here I am showing you what happens if you have a multi-loop CISO control strategy here, and let us say that this process is at steady state right now, and from the customer the demand from the customer what it says is that there is some sort of a set point change which has to be done. So you want currently you are operating at, let us say, 0.5 fraction, and then you want to change it to 0.51 because some specification has changed downstream. So because of that this AIC controller will get triggered, because now you want to increase the purity of this stream. So because of that you would want to increase the amount of W1 which goes into this particular blend. So this AIC will increase W1, But now you can see that as you have increased W1 and W2 was kept at its steady state value, the addition of these W1 and W2 goes beyond W. So, the second controller, which was the flow controller, will try to cut down W2. So, as it does that, it will try as it reduces W2, W will be maintained, but as you have put in less amount of W2 and more of W1, your X will again increase. So, what you can see is that these two controllers will try to they will try to catch each other. So, every time one controller satisfies its objective, the other controller gets disturbed, and eventually they will have to find a what is known as a sweet spot, where the addition of W1 and W2 would still make be equal to W, which is a set value, but the ratio of these two will ensure that X is also maintained. So, let me show you what happens or how these responses look like if I simulate this particular system. So, here are the simulation results. The top two curves show the two controlled variables and the bottom two show the two manipulated variables. So, you can see that I had made a small set point change in terms of X. So, because of that your W1 increased. As W1 increased, your W also increased. So, the other controller started reducing W2 and the first controller increased W1. But while doing that, you can see that some significant oscillations are introduced into the system, and what I am showing you is a final optimized controller strategy. If I use or change the controller parameters, it is also possible that these two controlled variables do not converge to the set point value, but the oscillations start increasing. So, there are growing oscillations for certain values of controller parameters. So, such kind of what is known as instability can also occur when you have such kind of interacting seesaw control loops. So, when you want to do such kind of a multi-loop seesaw control strategy, it is easy to implement, but very difficult to design. So, what do I mean by design? If you want to design such kind of a multi-loop seesaw strategy, first and foremost what you have to do is you want to dedicate one input to one output. So, the way I have shown you here, if I have two controlled variables and two manipulated inputs, I want to decide first that U1 will be decided based on Y1 and U2 will be decided based on Y2. So, when you want to do that, there are certain factors which you want to incorporate. One is that U1 should have direct effect on Y1. Because that is obvious that if I am dedicating this particular input to control this variable, there should be a direct effect so that this particular controller will be fast. And at the same time, what you would want is U1 does not affect Y2 or any other outputs. Now, this is a very idealistic assumption, and if that was the case, then this strategy would work perfectly. But in reality, what happens is, even you can see from the previous example of inline blending, when you change U1, it not only affects Y1, but it also has an effect on Y2. So, what happens is, when you find a variable which has a direct effect on Y1, you also want to minimize its effect on the other output. So, rather than having does not, you will try to minimize effect on other variables. So, that is sort of known as design based on minimum interaction. So, you want to minimize interactions between two controllers. So, ideally you would want that when your controller 1 is acting, it should not affect controller 2, but as long as this U1 affects Y2, this controller will also get affected. So, when you want to dedicate these input output pairs or decide these input output pairs, you want to ensure that the interactions which are happening between these controllers, they are minimum. So, for that, first of all we need to find out how do we quantify these interactions. So, there are some ways in terms of quantifying these interactions. So, we will try to see how do we go about it. First, we will look at a very simple 2 input 2 outputs MIMO system, and we will try to extend the analysis which we have done earlier for a seesaw strategy to this multi-loop CISO strategy. So we'll consider a 2-input, 2-output system. So earlier when we had a single input and single output, we had a single process transfer function between input and output. Now you have 2 inputs and 2 outputs, so you will realize that you require 4 process transfer functions. So this is GP11, GP12, GP21 and GP22. So GP11 represents the input of U1 on Y1, GP12 represents the effect of U2 on Y1, GP21 represents the input of U1 on Y2 and GP22 represents the effect of U2 on Y2. Okay. So now here what we have assumed, so based on this, if I want to write the equations, what I will get is my Y1 Y2 is given by GP11, GP12, GP21 and GP22 times U1 and U2. So your Y1 is equal to GP11 times U1 and GP12 times U2 because both inputs affect the output, and same way Y2 will be equal to GP21 times U1 plus GP22 times U2. So in this figure, if I want to find out what is my final Y or final Y1, it will be the summation of these two contributions. Similarly, Y2 will be the summation of these two contributions. So that will be my open loop representation of this particular system. Now let us see how do we incorporate control into this. So I have said that in terms of control, I am going to dedicate Y1 to control U1 and I am going to use Y2 to manipulate U2. So let me also represent here U1 and U2. So this U2 is going to go here and here, and this U1 is going to go here and here. So all I need to find out is U1 and U2. So let us say you have a controller, I am dedicating, so there will be a measurement of Y1 and then that will be compared with the set value of Y set 1, then you will have a first controller GC1, you will also have a wall GV1 and then it will give you U1. Similarly, you will have measurement of the second variable, you will have the corresponding Y set 2, you will have GC2, GV2 and then Y2. So you can see that your final multi-loop CISO strategy will look like this, where you have dedicated one input to one controller. This controller deals with Y1 U1 and this other controller deals with Y2 U2, and you can also see that there are some lines which are going across these two controllers, and therefore that is why it is going to result in some sort of interactions. So for this particular system, how do we get the closed loop response? So the open loop response, so when I showed this was your open loop response. So again we will limit ourselves to only servo control for an example. So for a seesaw strategy, what we had was if I want to see how my output in the closed loop changes, it was GC GV GP over 1 plus GC GV GP GM. For multi-loop seesaw strategy, what you will get is this y1 y2. You can simply extend it in the same way. This was for a single input single output. For this multiple thing, what you can write it as is this multiplied by inverse of this. So, what you get is 1 plus GC1 GV1 GP11 GM1, 1 plus GC2 GV2 GP22 GM2, inverse of that, and then you also have the cross terms like G21 GC1 GV1 GM1, and this will be G12 GC2 GV2 GM2. This will be multiplied by this vector about G11 GC1 GV1, G12 GC2 GV2, G21 GC1 GV1, and G22 GC2 GV2 times y set 1s and y set 2s. So, you can see that it is simply a extended version of the same formula. And now let us see the interesting thing. So, when you had two single loops, so if I assume that y1 u1 and y2 u2 were two separate problems, if I want to ascertain the stability of this system, then you would want to solve the characteristic equation which will give me the stability of that system. So, for the first thing it will be 1 plus GP11 GC1 GV1 GM1 equal to 0, and for the second controller it will be 1 plus GP22 GC2 GV2 and GM2. So, if these were two separate problems, then that is what you would get as a characteristic equation. But for the multi-loop seesaw strategy, where additionally there are two more transfer functions, the characteristic equation is given by the determinant of this first matrix. So, this particular matrix, its inverse. So, finally, when you expand this in terms of the cofactor expansion, what you will realize is in the denominator it will be the determinant of this matrix. So, that is what will decide what is the characteristic equation for this system. So, characteristic equation is given by the determinant of that particular matrix, and it comes out to be 1 plus GP11 GC1 GV1 GM1. So, which is the first characteristic equation which I had written earlier, plus 1 plus GP22 GC2 GV2 GM2 minus a cross term which comes out to be GP12 GV1 GC1 and GM1 GP21 GV2 GC2 GM2. So, what you can realize is that this particular characteristic equation, so its solution is different than considering these two solutions. So if I assume that these two controllers are operating independently, that is wrong, because if I design these controllers assuming these design this control system by assuming these two controllers to be separate, what I am end up having is a characteristic equation which satisfies these, but the real characteristic equation also has this additional term. So this is known as the interaction term. So this term is gonna cause the interactions into this system. If this term is 0, then automatically the characteristic equation comes out to be this multiplied by this equal to 0. So automatically it tells me that the two characteristic equations are same as assuming that the original system can be thought of as two independent loops. So you can see that this particular extra term is going to cause the characteristic equation to deviate from the fundamental characteristic equations of two separate control loops, and that sort of quantifies the interaction in this system. So where does this term comes from? So let me show it to you through the same diagram which we had seen earlier. So if you recollect what we had talked about earlier, what we generally get this characteristic equation from is from the closed loop behavior, that one comes because you have a negative feedback. So every time there is a closed loop, you will get one term of that corresponding closed loop characteristic equation. So you can, if I ask you a question, how many loops are there in this particular figure, that will give you an answer about the interactions. So let us say I want to find out the loops. One is an obvious loop. Let us say I start with this u1 and I move this way. You can find that this is loop number 1. Similarly, I can start with u2 and I can find that this is my loop 2. So if these were the only two loops in this system, then the characteristic equation would have been the characteristic equation of this loop multiplied by this equal to 0, and that was the case I told you about when we did not have that interaction term. So where does this interaction come from? For that you have to look at the third loop. So let me just trace it down for you. So let us say I can start with u1. So I move it this way. Then I go to y2, and then from here I have to go here, and you will see that I will finally close the loop this way. So there is a additional loop which is a third loop which causes that interaction term, and this loop goes through the transfer functions like gp21 and this gp12. So as long as you have these transfer functions known as cross transfer functions, if any one of those transfer function is non-zero, your two control loops will interact. Now note that this loop will not be formed if either this or this was equal to 0. So you don't necessarily need that both these cross transfer functions should be there. Even though one of them is 0, then you would not have this third loop, and then your interactions in the system will go to 0. So this is the third loop which gives you interaction between the two control loops, and it will be quantified by that big term which I had in that closed loop representation. So what take home message I want to give you from this is that when you have these multi-loop seesaw controllers for a system which has multiple inputs and multiple outputs, these are easier to implement, but what happens is the stability of this system depends on the other loop. So if I want to design a controller for this u1 and y1 pair, I also have to look at how the other controller is tuned. So that kind of interaction or that kind of decides the final stability of the system. And as I said for the previous example of inline blending, what happened was if I change one of the control loop parameters, the same stable system can also become unstable in terms of both the controllers. So the controller properties of one controller affects the performance of the other controller. So that is why it is important to make sure that when you find out this y1 and u1 pair, the interactions between them are minimized. So we will focus on that in the after the break. So thank you.